All right. So, I mean, we're both kind of talking today.
Yes.
So.
All right. We're going to try to make this more conversational than normal. I'm going to turn off my camera so you're not looking at two of me. And also because this one's like aimed almost directly up my nostrils. So that's going to be in the recording. All right. But I think we're going to try to work on my screen.
Yeah.
So hopefully that's not too confusing.
You have it open.
I have it open, so.
Okay.
No.
Uh,
This is my second technical difficulty in a talk this week. Let me try again. There we go. All right. Density operators. So what is a density operator and why do we care? That's our first most important point. So a density operator, or equivalently a density matrix, is one way. I hope y'all can read cursive because that's like how I write. So if not, you'll be able to read whatever Zach writes. So a density matrix is a way to describe a quantum state. Okay, well that's all fine and dandy, but we already have a way to describe a quantum state using our state vectors. So why would we ever want a density matrix or a density operator? Well, as the name says, it's a matrix, first of all, versus our states, which are vectors. So the type of description that you get is slightly different. They're mathematically equivalent. I think that's important to note. So mathematically, everything you can do with everything you can do with your vector description, you can do with your density matrix description, and vice versa. There's just for certain applications, it's technically easier to use the density matrix application.
I'll prove these are equal or equivalent later.
Yeah, which is good because I'm here for the wishy-washy intuition and you're here for the hard math. So, all right. So they're mathematically equivalent, but the density matrix or density operator, which we normally will call rho, so that's in comparison to our ket. So this rho, this lets us describe a larger variety of states in a convenient manner than just these kets do. And you can quickly turn a ket into a density operator by just taking your outer product, it's called, where this is not an X, that's me being, like, that's just me being shorthanded, but this is a ket bra. And so you can turn any vector into your density matrix pretty easily. But although it's very easy to describe a pure state or a vector using the density matrix description, we'll come to see that it's not as easy for some density matrices to describe them using the pure state vector description. Intuitively, what does that look like, right? So we've talked before about your states living on the block sphere. So let me draw my block sphere real quick. We have 0, 1, near plus or minus or somewhere along a diagonal. And we've said before that we can describe our state psi as living on the surface. So psi lives on the surface somewhere here. But what about everything inside of the block sphere? Is that an acceptable quantum state? Well, it turns out yes. However, describing them using this sort of ket notation is actually extremely difficult because the states on the inside are not pure states like this that you can just describe with one vector, but a combination of states. So what does that mean? So we say that if it lives on the surface of the block sphere, that's a pure state. And if you make it through some sort of mixture of an ensemble of pure states, then it's a mixed state.
But Marguerite, what do you mean by a mixture of pure states or ensemble of pure states?
Mathematically, or do you want to do it? All right.
Well, we just give
Okay.
like the description of it, and I'll write it later.
Okay, well, yeah. So by an ensemble of pure states, what do I mean? I mean, literally you have, I don't know, maybe some index of pure states, I, and then we turn them into density matrices for convenience. So that you do that just through this description. And then you say, all right, well, now I have a probabilistic mixture of them perhaps. And if you have this sort of setup for your density matrix, then you can in principle have, you know, some mixture of mixed states, but
Mixture of pure states.
a mixture of pure states. Thank you. You could also have a mixture of mixed states, but you know, so a mixture of pure states like this, then it isn't necessarily true that there's like one convenient pure state that you can decompose this into, such that I'm not go ahead. We're going to call this phi. I don't know. It's not necessarily true that there exists some phi where that is equivalent to this, right? One singular phi. And that's kind of what I mean by a mixture. And all those states live inside, not on the surface of the block sphere. And you can notice just from your conceptualization of a sphere that the surface of the sphere is not going to contain as many states as the entirety of the inside. So in principle, there are many more mixed states that you can have than pure states.
Can I say something about the ensembles?
Go for it.
All right.
I don't know if you want the pen,
Sure.
because you can actually
Do I have to press anything?
no, if you
Okay.
press the button, it turns it into an eraser.
Okay, cool. Just move like this. Okay, so so a convenient notation for the ensemble is like this, and it kind of shows what is meant by it. So you have a list of pure states indexed by I here, and you don't know which pure state you have. There's a certain probability of having each pure state. And so the way we can't represent this as you know, something of the form alpha 0 plus beta 1, for example, but we can represent it as a density matrix. And so that's why this formalism is important. That's where it comes in. But anyway, so what? Oh wait, where's the button for the eraser? This one.
Yeah.
Aha, neat. Okay, but what we were saying earlier was there's an equivalence between this and the density operator, which is given by just the probability from here and the state from here, and you make the projection operator here, and you multiply it by the probability, and you sum them up. That's exactly what the density operator is. So a pure state is just an ensemble like this, except there's only one probability here, and it's equal to 1, and there's only one state here. All the other probabilities are 0 if you want to include other states. And so what you get is just something that looks like psi, psi. Okay, go ahead.
Quick note, and this is like a kind of a departure from density matrices, but the book doesn't ever describe them as a matrix. But if you have, a psi AB like this, then the outer product you can write as AB and then A star, B star, right? Also notice you can like fill in these blanks. This is a trick someone taught me, and I'm just like sharing it with y'all. But just like writing them in this manner, and then you can like read them off like a grid. And I always just think that that's so cool. Just like, oh my God, this is just make my multiplication easier. All right. This is not super important to what a density matrix is, but I'm just showing you how you could calculate one really, really conveniently. All right, Zach, I have a couple of questions for you. Do you know how you might get a mixed state?
You might get a mixed state.
How do you get a, so we said like, okay, so there's a difference between a mixed and a pure state, but like, how do we end up getting one, right?
Well, I mean, so if you have a pure state, you know exactly what state your particle is in.
Yeah.
Right. It may not be an eigenstate, so when you go to measure it, suppose you have a pure state. If you go and measure it, then it collapses to either, for example, in the computational basis, the 0 state or the 1 state. But for a mixed state, there's even more ambiguity. So you don't know what state you're starting off in. So there's some probability you're in state, psi 1, some probability you're in state psi 2, and so on. So a situation where that might happen is, I don't know, can you think of a physical?
Or you don't know what state you're in to begin with.
Yeah.
I mean, well, the book gives you an example. So you might have like, I believe it's like 3/4, 0, 0, and 1/4, 1, 1. And you might naively think that this is equivalent to, square root 3/4, 1, 0 plus 1/2, 1, 1. And you might think that it's this one side, but in fact, you can get it a different way. And one good way to think of how you might get this is like, this is obviously a quantum mechanical state, right? It's a quantum mechanical mixture of states, but you can think of a classical mixture of states, right? So you might have, I don't know, a bag of zeros and ones. This is how I always describe it. It's not completely physical, but, and then you pour out like 3 parts of 0 to 1 part 1. And so that's a purely classical mixture that you've created, and it's not at all equivalent to this state.
I guess even simpler would be just have a bag of particles, right? And they're all prepared in one of, I don't know, let's say 4 states. And Alice just grabs one out. Then the state of her system is some probability that she would grab that particle, plus some probability she would grab the other particle, plus some probability, all multiplied by the projection onto those states.
Right.
Yeah. So
so it's like a density matrix you can describe using classical probability as well. So it could be described by classical probability like this, or it could be a quantum mechanical probability like here, right? And so there's some ambiguity. You don't know necessarily in some cases which one that is. Another way to get it, which the book alludes to, and I think that we can talk about a little bit later, is you can also just like not fully know your state. You might know your part of the state, but it might be defined on more Hilbert spaces and you don't have access to them. And so that might confuse your knowledge of the state a little bit as well. Okay, so that's pure states and mixed states. Do you want to talk a little bit about some fun facts on what makes a density matrix?
So okay, I guess you're going to talk about postulates. So
yeah.
Do
you want me to take postulates first, or?
Yeah, just give the postulates first, I guess.
All right. Okay. So here we go with postulates. So you can reformulate all your postulates of quantum mechanics using this density matrix description. Though we do have to note a few things about density matrices first. So these are just, you can kind of think that these define a valid density matrix. But one, we always have that your trace of rho is equal to 1. So if you haven't had linear algebra and you don't know what a trace is, it's for a square matrix. I don't think it's defined for anything but a square matrix, right?
It's just the sum of the eigenvalues.
Oh, okay. I thought it had to be square, but yeah, so you have A1 through AN, what have you, and then you don't care what's not on the diagonal. The trace of this is just the sum of the diagonal. So
it's a theorem in linear algebra that the trace is also equal to the sum of the eigenvalues, and that's a basis independent definition of the trace. It's the one that mathematicians prefer. But
this is the one physicists always use, right?
Yeah, but these things are equivalent, and there's a proof of that somewhere. But
yeah. Okay, so this is your first fun fact, is that your trace of rho is always equal to 1, and I guess it's like the equivalent of the normalization factor we see in vectors. But so you have that, and then you also have that rho is positive semi-definite. So little bit of
what does that mean?
Yeah, let's go back over this. I think we touched on it 2 weeks ago, but like very quickly. So positive semi-definite is like a greater than or equal to for a matrix, as you can see here. But the only caveat that I think we forgot to mention before is that this only applies to the eigenvalues. So this means that the eigenvalues of rho are all greater than or equal to 0.
A mathematician would define it slightly differently.
You're a mathematician, feel free to define it
All
slightly
right, let
differently.
me define it slightly differently. So rho being positive semi-definite means that for all phi in our Hilbert space, the quantity phi rho phi is greater than or equal to 0. So this is the inner product of phi with rho applied to phi. So remember, rho is a matrix, phi is a vector, so you can apply the density matrix to the vector, which sounds odd because the density matrix contains like
A state, yeah.
but it's doable.
Yeah, this is also a cool way you can kind of make states act like operations too, which is weird. But yeah, so when we say it's positive semi-definite, we mean its eigenvalues are all greater than or equal to 0, or this case, this like every expectation value, I guess, is greater than or equal to 0. But you could in principle have like negative off diagonal terms. So it doesn't mean every term in the matrix is greater than 0. And I think that's the big caveat, right? Because I mean, I think you can have like up to something like this. Well, 1/2, whatever, for the trace thing. But and this is still, I think, positive semi-definite.
I'm not sure.
I don't know. I don't necessarily quote me on that. Yeah, okay. But the important part is that it's not every element, but eigenvalues or expectation values. All right, so now that we have these two facts, that it's, trace is equal to 1 and it's greater than or equal to 0, we can define our postulates in terms of it. So postulate 1. I'm sorry, I'm going to have to read my terrible handwriting for all of this. So postulate 1 states that any physical system still has a Hilbert space corresponding to it. So a Hilbert space is a vector space with an inner product, right?
Yeah, in finite dimensions, it's always complete. So
yeah. So any isolated physical system, and the state on this system is now specified by some density matrix. So some rho such that rho is positive semi-definite and has trace 1. So it's a valid density matrix. And if the system is in some composite, not composite, but some other state rho I with probability pi, then you can write the state of the system as a sum over all of the possible systems. So apology if my p and my rho look very similar. Okay, so this is your first postulate, which basically says, hey, we have a Hilbert space and we have a state that lives in that Hilbert space that describes our system. Okay, so postulate 2, electric boogaloo. So evolution of a system, so say from i.e. from some T1 to T2 is described by a unitary transform. And technically speaking, this is only for closed systems. So closed transformation. Okay. And so if we have rho at T1 and rho prime at T2, then rho prime is equal to rho conjugated by a unitary. Are you going to describe the unitary thing?
So notice that this is not quite the same as the ket notation, right? So remember for the postulate when we were working with just kets, psi prime was given by the unitary u times psi, and there was no u dagger on the other side. But this was for pure states. So what happens if we write this in density operator notation? Well, we get psi prime, that's my density operator for psi prime, is equal to u, oops, that's
an H?
u psi times u psi dagger, which is equal to u psi u dagger. So we get the u dagger here from going from the pure state to the density matrix. So to see that this is true in general, you just take sums and distribute things linearly. And what you get is something that looks like that.
Mm-hmm. Yeah, and when I say conjugation by unitary, this is also the form that I mean, that you put the u and the u dagger on either side.
Oh, yeah.
So I think that terminology is fine. No one's ever stopped me from saying it, so. All right, yeah, so that's postulate 2 is that we're still going by unitary evolution. So postulate 3 should be about measurements. I know how to spell. So measurements are described by measurement operators.
So there has to be a separate postulate for measurements because your system, when you make a measurement, is no longer closed, right? It's
Right.
interacting with something outside of its environment. You could extend your system to include whatever measurement apparatus you have, and then actually the evolution would follow postulate 2. It would be a unitary evolution. But if you don't extend your Hilbert space, then you have to deal with this wave function collapse.
Yes. Thank you for that explanation, Lauren, because you're writing the postulate down. But so okay, yeah, so we have some set of measurement operators now, m sub m, where the little m corresponds to your outcomes, and your probability of getting little m is going to be given by now a trace. And so the book just goes ahead and gives you this, which I think it's not clear why this is your outcome, but so trace has something called a cyclic property, which means if you have a full trace, everything that's inside of your brackets can be cyclically moved around. So I can take this M dagger and move it to the back, and then you get, and then they have a little M attached. Now you get a conjugation by M dagger, and I think it looks a lot more like your unitary evolution that we've described before.
But you can also see why this would be true for a pure state, right? So if rho is a pure state, then it can be written as the outer product of psi with itself for some pure state psi. And so what we get here is, I'm just going to use this form. This is the trace of m dagger, m psi, and using the cyclic property, well, I mean, just using the trace property, really, you write this as psi, I missed a trace. There it is. This is the trace of psi, m, m dagger, m, psi, but this is just a number.
And the trace of a number is just a number.
Exactly.
Yeah.
But this is exactly what the measurement postulate was for a pure state. And so this is consistent.
So with that, I think that takes us to postulate 4. Yes. Oh, one more thing is that we still have the completeness criteria where summing over all of your measurement operators, this should be. Come on. M dagger. This should give you back identity, right? Okay. With that, postulate 4 says the state of a composite system is the tensor product of the states on all of the component systems. So if you have some state defined on some Hilbert space 1 through n, this is just equal to rho 1 n tensor, or rho 1 and tensor product rho 1 2 tensor product tensor product rho 1 n. It is not okay. So note too that this is equivalent to doing a tensor product on these Hilbert spaces, and this is fine to do for a density matrix. But you can't do something equivalent to this for a pure state, because that is only true for a pure state if it's a product state. It can be written as a product of independent states on Hilbert spaces. Any further comments on this one? Okay, cool. So these are your 4 postulates. So they're pretty much the same, except now we have a density matrix. And yeah, I think Zach did a pretty good job of arguing for why they're all equivalent.
Okay. You got anything else?
Nope, not for that part.
Okay. So let me argue about why the what are they called? The ensemble of states, ensemble of pure states, is equivalent to the density operator. So let me more or less give you a proof. So let's see which direction I'm going first. So suppose you have an ensemble like this, then you can construct a density operator as follows. And we can check that this thing does indeed have trace equal to 1, and it's positive semi-definite. So the trace of rho is equal to, well, it's the trace of this sum. But the trace is linear, so we can pull out the constants and the sum symbol. And so this is the sum over I, pi, and the trace of this is just the inner product of psi I with itself. Oops, I gotta find the button again. But this is equal to 1. We assume that they're normalized. But the probabilities have to sum up to 1. So this is indeed equal to 1. Okay. So it satisfies the trace equals 1 criterion. Now we want to check that it's positive semi-definite. So we let phi be any vector in our Hilbert space. Then we sandwich rho between phi and itself phi. Okay. Then this is equal to phi, and then rho is the sum over I of pi, psi I, phi. I'll just write it like this for a second. And we can push these phi's inside. This is the sum over I, pi. We have phi inner product with psi I. And then psi I inner product with phi. But this is the conjugate of that. So if we remember a little complex analysis, this is the inner product of phi with psi I modulus squared. And the point is that this thing is greater than or equal to 0. And this is a probability, so it's greater than or equal to 0. So the whole thing must be greater than or equal to 0. And so that's the first direction. So conversely, suppose the trace of my matrix rho is equal to 1, and it's positive semi-definite. Now I want to prove that this thing comes from an ensemble of pure states. So since rho is greater than or equal to 0, Roy mentioned last time, was it last time? I think so, that positive semi-definite operators are Hermitian or self-adjoint. And we kind of doubted him. Sorry, Roy. Roy was correct. In finite dimensions, this is always true. You run into some problems with infinite dimensions, but we're only worried about finite dimensions here. Okay, so since this thing is positive semi-definite, that means it's Hermitian, and Hermitian means normal, and normal means we can apply the spectral theorem. The spectral theorem tells us that this thing has a spectral decomposition that looks like, what notation did I use here? Well, I use J, but let me just use I. So it looks like this. Okay, for some states I and the eigenvalues lambda I. So I guess the I are the eigenvectors.
States I?
They should be, yeah. And the spectral theorem, well, because the thing is positive semi-definite, and these are the eigenvalues, that tells us that these lambda I are in fact greater than or equal to 0. And in fact, since the trace of rho is equal to 1, right, we're assuming this, that tells us that, so if we take the trace of this, what is it? The trace of rho is equal to the sum of the eigenvalues, right? This thing becomes an inner product, which is equal to 1. And this is equal to 1 by assumption. So if this is positive and it sums up to 1, well, then these are our probabilities. Okay. So a ensemble of pure states for this density operator would be lambda I. And so that ends the proof. So the ensemble of pure states is equivalent to the density matrix. So you could use either one, but the density operator seems to be really convenient in a lot of cases. Okay, and the other thing I wanted to do was answer a question, which is if you're given a rho, how do you know if it's a pure state or a mixed state? So pure versus mixed. Well, if you take rho squared and you take its trace, well, what if rho is a pure state? So let's assume that rho is pure for a second. That means that we can write rho as psi for some state psi. My psi's look terrible. They just look like down arrows.
Well, as long as you're consistent in your terrible size, it's fine, right?
So this would be the trace of psi, oops, and
that's an expectation, right?
Yeah, psi, and then we multiply it again because we're doing rho squared. psi, psi. Now this psi inner product with that psi is 1, right? Because it's normalized. But this is equal to psi inner product with psi by the definition of the trace, and then that's equal to 1. So if rho is a pure state, then the trace of rho squared is equal to 1. We can also show that the trace of, so when rho is a big state, then the trace of rho squared is less than 1. So this is easier to see from the eigenvalue perspective. So if lambda, so if the lambda I, if these are all eigenvalues of rho, let's say they have eigenvectors I, so that's another list, then rho squared has eigenvalues lambda I squared. So the proof of that's simple. If you take rho squared, multiply it or apply it to I, well, this is rho times I. But since lambda I is the eigenvalue of rho with eigenvector I, this is equal to rho times lambda I. This is just a number, so we can move it to the other side. This is lambda I, rho I. And then we do the same thing here. This is lambda I times the vector I, which is lambda I squared times I. So every eigenvector or eigenvalue of rho, when you square it, gives you an eigenvalue of rho squared. And since they're the same size matrix, well, you've exhausted all the possibilities for the eigenvalues, right? An n by n matrix has, yeah, some of them could be degenerate, but so there you go. So what does this mean for us? This means when we take the trace of rho squared, well, this is the sum of the eigenvalues of rho squared, which are lambda I squared, right? So if rho is mixed, then that means that the lambda I, each of these is less than 1, right? Because if it were pure, then you would have only one eigenvalue, which is equal to 1, and all the other ones would be 0. So if it's mixed, then these are all less than 1. So that means this is less than the sum over I of lambda I, which is equal to 1, right? So if you take something between 0 and 1 and you square it, it makes it smaller. So that's where this inequality comes from, right? Okay, so that proves that the trace of rho squared for a mixed state is less than 1. So if you're given a density matrix and you want to know if it's pure or mixed, take its square, take the trace. If it's 1, then it's pure. If it's less than 1, then it's mixed. Okay. So that's a really handy theorem. All right, you want to do partial trace?
Yes. Okay. So I had a couple last notes for the mixed state versus pure state thing. So first of all, just some fun facts about, and these are exercises in the book, so I'm not going to work them out for you. Well, I'm going to pretty much work one of them out.
I have them worked up. If you.
Okay. So first point is talking about the block sphere again. So there is an equivalent way to talk about how previously on your block sphere, that is a terrible sphere. Okay, so previously on your block sphere, you could describe your point on the surface via a variety of angles. Well, there's an equivalent way to describe a mixed state on the block sphere. So you can write any state rho as a mixture over your Pauli matrices, specifically 1/2 your identity or your Pauli 0 plus some vector r times the vector formed by the Pauli matrices. So this vector is sigma x sigma y, and sigma z. And R has the property that it's contained in real numbers, so R3 specifically, and has magnitude less than or equal to 1, right? As you would hope, because that will preserve our trace equal 1 if you don't see that. So R then is called your block vector. Okay, and so your block vector now tells you where in the block sphere your density matrix is. And there's one in particular, which is often of note if you want to check algorithms or other things. And that's when R is identically equal to the 0 vector. And so basically all of your weights are 0, and you get rho for a single qubit is 1/2 your identity. Okay, and this is called your maximally mixed state. And where is it on the block sphere? Well, R being 0 and all of its components tells us it's at the dead center. Okay, so your maximally mixed state is sometimes thought of as your most classical state. It's a state you can make by just taking mixtures of your basis state, and it's defined. It's essentially a tensor product for all of your spaces. But say you have n qubits, then your maximally mixed state, which we sometimes call pi, is defined as pi tensor to the n, which means essentially you tensor it with itself n times. This is always equal to 1/2, the number of qubits, times your identity on that number of qubits. So that's one interesting state to know about. And you can, for a lot of information processing tasks, you can kind of think of this as the most useless state you can have. It's your least quantum mechanical state. So we can then talk about, all right, now that we know what a maximally mixed state is, I want to talk a little bit about a reduced state. So we said one of the ways you can get a mixed state is you can have limited knowledge. So say rho AB is defined on two systems. A and B. And oftentimes you'll hear people call this Alice and Bob. And the other names other than E are just kind of free-flowing. If you can think of a name that starts with that letter. E is always Eve, because it's typically used as an eavesdropper.
Let's use Charlie and Dum Dum. Charlie and Dum Dum,
right. So this generalizes all the way up to Charlie and Dum Dum, but and even all the way to Z, where you might have a Zach. But we can define the state on the subsystem A exactly by taking a partial trace over all the systems that we don't have. And why would we want to do this? Well, maybe you're only Alice. So in system A, this is your state, rho A. If you're only Alice and you don't have access to Bob and any of his qubits, his information, then you can't fully describe the state of the system. And this is the mathematical description of how you do that. So essentially you take a trace over just Bob's system and you say, we've traced it out and it's no longer available to us.
What does that look like?
What does that look like? That's great. So when you do a trace, and I know it says like you just sum up over your diagonal, but really what you do when you do a trace, so a full trace over rho AB, this is equivalent to sandwiching it by the basis states. So you might have I, J, I on A, J on B for whatever your basis is, rho AB. And it's pretty common terminology or common notation to just write what Hilbert space you're talking about at the bottom right of your state. That's, where's the button?
Use the fix all my problems button.
Exactly. So erase everything I wrote. So technically, if you want to write everything in bracket notation, you define a trace like this. So you have your state and you sandwich it by your basis vectors, and then you sum up over all of the sandwiching by all of your basis vectors, essentially. And this gives you a number, 1 specifically, because it's just the trace of your full system. However, if you do a partial trace, so now we denote that by just having one of the subsystems listed here, then what does that look like? Well, now you only sandwich by the system on B. And from our previous postulates, we know row AB can be described as a tensor product. So row A, tensor, row B. This guy can't hit this guy?
Not in general, right?
Not in general for like vector descriptions, but these can be decomposed into combinations of pure states.
I don't think the tensor product holds in general. I think that's what they call a product state. But
if this was a pure state, you would be correct.
Yeah.
I
I think
maybe they have like weights to them essentially, but they will go. Oh, you will.
They have a combined weight is the problem. So you can't just split it up. So you have to write it as like so row AB is like a sum, and then some probability P. I'll put the index in a second, but there's like a system A, I, oh God, I1, I2, then you tensor J1, J2, and this depends on I1, I2.
Yeah. Whenever you
J1.
take, so inherent in the tensor product formulation, whenever you break them up like that, you are adjusting with new weights, such that whenever you tensor product them together.
I don't believe that, but continue.
It's literally in Nielsen and Schwab. Double check me.
No.
All right. Okay. So anyway, when you do this, row A gets to just pop out because it's not being affected by any of the operators here. And you'll just get, you'll have row A, and then you'll have the trace of B on row B. Got my summation here. But this is just a trace on a state, which is equal to 1. So then you'll just get back row A. If you break it on to composite systems. So this is how you describe the partial trace. And feel free to double check me if you don't believe about breaking this into the tensor product, but it is the formulation used in Nielsen and Schwab. So, and that's the text you're following. Okay, but okay, so now that we've defined a partial trace, how can I use this to describe how you can get a mixed state? So once again, we have row AB defined on systems A and B, okay? And suppose it's of a particular form where it's a maximally entangled state. So we've seen those before. I know what I'm doing.
Okay.
Yeah, okay, I knew exactly what you were worried about. Okay, so you can form this way, and then this, you can double check me. This should be your Bell state, right?
They use some other notation. I don't remember what it is.
They use, I think this is, they call them beta 0, 0.
Yeah, that's what it is.
Beta 0, 0. Yeah, like that. Okay, so this is a pure state. I just wrote it in terms of one vector, so that's a good giveaway. And then the way you write this out is like this. So you FOIL these things like you learned in grade school.
Good old FOIL.
It never goes out of style.
Back when life was simple.
Well, apparently life is still simple because we're still foiling. All right, so you get this state. This is your state, row AB. Now, what if we lose Bob? What if Bob decides to burn his lab down? What is the state that we have left over now?
Push Bob and his qubit into a black hole.
He had it coming. So now we're tracing out Bob from existence. And what does this look like? Well, we're going to sandwich by our states. So we're going to have 0 on Bob. And up here, I'm using the convention that Alice comes first and Bob comes second, because that's how alphabetical order works. If I could stop hitting the eraser button, that would be great. All right, so you're going to have 0 on Bob times row AB, sandwich like that, plus 1 on Bob, row AB, 1. And so that's kind of a concrete example of what I meant here by like summing over a sandwich of all your basis states. Okay, so we're going to go up here and we're going to say, okay, where does this give me something that's non-zero? So 1/2. Bob has 0 in both of these, so you'll have 0 on Bob. This is going to look very messy at first. 0 A, B, 0 on Bob, and I'm just going to go ahead and distribute this through. I'm doing a lot of steps all in one because I noticed we're getting close to the hour. But this one should be 1, 1.
0, 0.
Yes. That should be, yeah, 0 for Bob. Plus 1/2
Oh, God.
dot 1. All right. I'm not going to write all that out.
Same thing with the 1.
Yeah, same thing with the 1. Y'all know what we're doing here. So we're going to get this guy's 1, this guy's 1. So that term survives. This guy's 1, this guy's 0.
You're only inner producting with the B state, right?
Yeah. Good catch. Rushing too much. So that survives, and then we keep the qubits on Alice's because Alice is still alive and well. So we have 0, 0 there. This guy is going to give us 0. This guy is going to give us 0. This guy is going to give us 0, right? And then you can imagine you'll get something similar. These 3 terms will all give you 0 here, except for this guy. So you're going to get 1/2, 1, 1 for Alice. So this is only on Alice's. And so this is now Alice's state post Bob being shoved into a black hole. And what is this state, though? I don't know, maybe matrix notation. Maybe we can put this in our block vector. Well, this is 0, 0. So, and this is 1, 1. So you can write that like this, and you can convince yourself through linear algebra that that's the case, right? So that's this plus this, right? And that'll give you these 2 matrix terms. So that's 1/2, 1 on your diagonal, but that's the identity. So you have 1/2 your identity on 1 qubit. That is exactly your maximally mixed state.
So notice you started with a pure state in a larger system, and then you took a partial trace and it gave you a mixed state.
Mm-hmm.
Because you lost information.
You have lost some information. In particular, if you start with a maximally entangled state, which is what we have with our Bell states, and you trace out one of your subsystems, you end up with a maximally mixed state. And it is true, however, that you can get a pure state. However, if you get a pure state after tracing out the other your other system, then it is the case that row AB is product. So that means that the Hilbert spaces are fully separable. Yeah.
Mhm.
So it's product if and only if, I know what you're grinning about, but you're still wrong. It's product if and only if your trace of A, trace over A of row AB is pure and trace, equivalently. These two things are pure.
So do you need both of those to be true or just one of them?
One of them being true will make the other one true, but I'm just writing them explicitly. So how is a state product? Well, you can see this pretty easily in the pure state case. So the state is product if it's defined on Hilbert spaces, A through, I don't know, Z. If it's equal to a tensor product for all letters, it's a bad notation on my part. It's a pure state on all of your Hilbert spaces, essentially. So if your pure state is written as a tensor product of pure states, distinct on your Hilbert spaces, then it's product. It's slightly more complicated on your density matrix side, because you can always write a density matrix in terms of pure states. So they're not in principle the same pure state. So for instance, for your density matrix, you might have on A, it looks like psi. Like how to formulate this. Your mixture might not be the same for all of them. I'm trying to remember how to formulate that.
Okay.
Yeah, anyway, we're out of time. So
last thing I would like to say is, if you have a mixed state, it's always possible to extend it to a larger system, which is described by a pure state. It's called a purification, right? So a purification is a density matrix whose partial trace gives you the original matrix.
So, so this purification, mathematically, that's just written this way. So this is the purification of rho. So you say this is on AB and this is on A. Your trace over your purifying system, or the extra bit you added on, if this gives you back rho. That's all a purification is. And you've literally made it into a pure state. That's why it's called purification.
Yeah. All right. Questions, friends?
I'm gonna click my.
I would like to suggest a topic for further study / research. I don't know if anybody's talked about this or done this, but the Bloch sphere is only for a two-dimensional Hilbert space. And if you try to generalize that to even one more qubit, then you have to deal with something four-dimensional, which we can't picture. So one question we can ask is, what are some ways to generalize, or not to generalize, to picture higher dimensional Hilbert spaces? So how can we construct something similar to the Bloch sphere, some kind of geometry like that would help us understand what's going on in higher dimensional Hilbert spaces?
I don't know. I already struggle with the Bloch sphere, I'm gonna be honest.
Well, there are people, not me, apparently not you, but there are people who understand this very well. Okay, so any questions from you guys? Stop the share, I think.
Do you want to stop the recording?
Yeah.
Oh, Roy's